Hello everyone, welcome again to Discrete Mathematics with me Adila Krishnadi, and now we continue our discussion on graph operation, and this time we will look at edge addition and removal. These two operations are actually rather simple. Edge removal is an operation where we remove an edge E here from the graph. So we denote this with G minus E, which is simply just removing small e from the set of edge E. Of course, you could do removal. You could remove multiple edges by doing this multiple times. The opposite sort of the opposite operation is addition. So you have an edge small e, not yet in the capital E, the set of edges, but this small e already connects u comma phi. Then you simply add G plus E, with simply just adding the small e to the capital E. So this is pretty simple. So to illustrate this, let's see an example. Suppose we have a complete graph with five nodes, A, B, and then C, and then D and E. And suppose we have complete graph, so let me just draw the edges here, here, and here. And now we want to remove the edge A comma D, and then let me just mark it here, this edge, and then this and then followed by removing sorry, I forgot one edge here. Two edges actually. We remove this edge, and then this edge BD, and then CD, which is this edge, and then DE, which is this edge, and CE, which is this edge. So what we get is a graph A, B, C, D, and E. Remember, we only remove edges in this case, so we don't remove nodes. We still have AB, AE, and then BE. We still have BC, but we no longer have BD, we no longer have CD, nor we longer have DE and CE. So this is the graph that we obtain. Now, what graph do we obtain by adding CE to it? Well, let's see, we have A, B, C, D, and E. With this is our graph. Then we edge C. So this edge, and then we add CE. So this one, so this is the graph that we obtain after we add C comma E to it. That's edge addition and removal. It should be pretty simple. A similar operation is node addition and removal. Here the operation, the node addition and removal, is slightly more involved than edge addition or removal. Well, I should say node removal is slightly more involved, right? So the why is it so? Well, the reason is because when we remove a node, we need to remove the corresponding edges that is incident at that node. So we need to remove not just the node, but also the edges incident at that node. So we define removal of a node phi by the removal of phi yields a subgraph G prime where the nodes the node phi is removed from capital V, so you get a new set of nodes. And then we simply remove an edge that is incident at V. If G is undirected, that means those V, so those E such that V is in ST of E. If G is directed, then we remove those HE such that either V is the source or V is the target. Meanwhile, adding a node, so node addition is very straightforward. You simply add the new node to the set. Now, let's look at an example here. So we have a complete graph with nodes A, B, C, D, and E. Like this, and then this and this. So what is the result of removing A? So you want to remove this, yeah, then that means we need to also remove this edge, this edge, this edge, and this edge, because those edges are the ones incident at A. So the result then is actually this graph, E, B, C, and D. Yeah, we simply draw them, yeah, and then this node and this node, right? So that's the resulting graph, and of course this is actually K4, right? So it is still complete in this case, right? So depending on the graph, right? If you remove a node from another graph, then yeah, you get. So here, so my point is that if you remove a node from a complete graph, the resulting graph is still complete. So that's node removal. Well, node addition is simple. Suppose we want to add a node F to this, we'll simply add F here, right? Yeah. All right, so that's clear. Now, the next operation is edge contraction. So edge contraction is a rather involved operation. So it is actually a combination of edge removal and node merging. So edge removal and node merging. So as a result, the result of this operation is not a subgraph of the original graph. Unlike, for example, edge removal, the resulting graph is still a subgraph of the original graph. So what is edge contraction? Edge contraction is defined as follows. Suppose you have a graph G, and E here is one edge in the graph that connects U and V. So remember, the small e here is in the graph and it connects the nodes U and V. Then contracting the edge E gives us a new graph G prime according to the following steps. First, we remove E, the edge is removed, and then we create a new node W and add it to V. And then for every edge E prime that is incident at U, yeah, then essentially we shift E prime to W. Yeah, we shift E prime, yeah, from U to W. So both in undirected and indirect graph. So in this directed graph, we just need to see the source and the target. And then finally we remove the U and V. So essentially the node W is the result of merging U and V. Yeah. So that's that's edge contraction. So let's see an example here. Suppose you have this graph with edge with 7 edges and 5 nodes. What is the result of contracting the edge E7? So this edge. Well, essentially what we have is we remove this edge. So we remove this, and then we merge these two nodes. Yeah, because E7 connects U and Q, right? So we merge U and Q to get a new node, and then let the remaining edges still involve, and we modified the remaining edges incident at U and Q. So the result is then you still have R here, yeah. You still have P and phi here is the edge E1. Now the result of merging U and Q, say let's say we have a node W here, let's call it W, and then E2 here becomes an edge from P to W. E5 becomes an edge from phi to W, and then E4 is an edge from R to W, this one. So let me write it. So this is E2, this is E5, this is E4, and E3 is also an edge from R to W. How about E6? Well, E6 was an edge between U and Q, but now because we merge U and Q, the result is you have an edge like this. This is E6. So that's the result of contracting the edge. Actually, if you look at the literature, there is some authors define contracting edge slightly differently. For example, some authors disallow the parallel edges and loops in the resulting contraction. So if the original graph is simple, then they want the resulting graph to be also simple. But in our case here, we don't make that restriction, and we simply just merge the node and and adjust the remaining edges. Now try this exercise for the edge contraction. This time we look at directed graph, but the principle is the same. Yeah. So we want to contract edge E8 here. So we want to contract this edge. So try this, and after you're done, we will discuss the solution in the next video.